Okay, so you've been out a bit, and I know you're probably panicking about what am I going to do. So my plan is this. I have a couple of videos that I think distill the information down that you've missed. And I forget exactly where you were. So the first one is one that I had done last year on the lab that you guys did with the series and the parallel circuit. Kind of goes back to the very basics. This next one that I'm doing right now is going to be utilizing those rules and kind of refreshing you with those rules. Within this, I'm also going to show you the next type of circuit analysis, which is something called Kirchhoff's laws. So we're going to take it one step at a time. I don't know how you're feeling. I don't know, your stamina or your ability to, do work. But if nothing else, you can sit, turn on the computer, watch it. May not be the most exciting thing on the planet, and get some idea about what to do. So here we go. So hopefully you've watched the first video, or you remember when we started doing circuits that we had two types, parallel and series, or one that chops up voltage, that's the series circuit, and one that chops up current, and that's the parallel circuit. So this circuit is obviously not purely either one of those. It's a combination. And if you look at it, always start on the positive side of the battery. If you follow this around, you'll notice you come to a place where the current's going to split. We call that a junction or a node. And that current will then split, come back together, and then come back around to the negative side of the battery. So no place do we have just a single path, and no place do we just have purely a parallel, like in this region right here. So what we're going to have to do is to decide, okay, bet your life on something that is purely parallel, or bet your life on something that is purely series. And that's where you're going to begin from. The whole goal for this exercise when you're dealing with these circuits is to, on paper, not in reality, but on paper, crush them down into the simplest possible circuit you can make, and then do your analysis from there. So I'm going to tell you where we're going to proceed. Well, I said when you follow this around, you come to this junction. During this junction, the current splits. Some of it goes through this resistor, some of it goes through this resistor. These parts here I call branches. So what you're looking for a purely parallel circuit is when the current splits, it passes through a branch, it goes through one resistor only, and then comes back to where the currents are going to come back together, or another junction. It splits, it goes through a single resistor, and it comes back together. So this guy right here is completely parallel. So what I'm going to do is I'm going to put a P, kind of like a breadcrumb trail, to remind myself that that's in parallel. So my goal is I'm going to compress these two. I'm going to shrink them down into a single resistor. Now, if you remember, or if you watched the other video already, when we put resistors together in parallel, we add them with this weird kind of inverse relationship. So it's inverse 1 over 100, and I'm going to drop the units off, forgive me, just so we can save a little bit of space here, plus 1 over 100. This is a 100 ohm resistor, this is a 100 ohm resistor. So when I add those together, I get 1 over R is equal to 2 over 100. But notice that this is 1 over R, not R. To make R, I'm going to say 100 divided by 2. Now I'm going to put my unit magically back on. So I get a grand total of 50 ohms. Now, an interesting thing to save yourself some time. If you see two resistors that are parallel, that are equal value, when you combine them to make a simpler resistor, it's just going to be half as big. Or if you had 3 of them in parallel that were exactly the same, their total resistance would be 1/3 as large, or 33 1/3 if it was this case. So I've made my move here to shrink this down. I'm going to now go to the next slide, and I'm going to redraw the new circuit with this compressed bit here. So it's going to look something like this. This one is the guy that we just compressed down. These are existing resistors. That was that 50 at the top, and this was the 25 at the bottom. And we said when we combine this comes out to be 50 ohms. All right, so again, we're not doing this in reality. We're doing this all on paper just to kind of do an analysis of the circuit. All right, so now we got to look at the circuit and we ask ourselves, what do we see that's pure? In this case, I see one path going from plus, oh, I think I reversed these, I'm sorry, going from plus to minus. If it's one path, that's by definition what we call a series circuit. There's only one path. And in series, the resistance is equal to the sum of the resistances. So in series, right, we sum up the resistances. So we're going to have 50, and again, I'm going to drop the units, I apologize, plus 50, plus 25. So I get a grand total of 125 ohms. Again, here we go. Grand total, and that comes back on. Okay? So I sum these up, and I'm now going to make the simplest possible circuit on paper that I can. This we call the equivalent resistance. So if I were to take all those resistors and crush them down to one, the equivalent resistance would be 125 ohms. I still have a grand total of 1.5 volts. That hasn't changed. Okay, this is what I call the compression phase. You crush this circuit down to its simplest form. Now, what we're going to do is go backwards. And we're going to go backwards, and I'm even going to change colors for this. Let me make it drastic so you can see it. Oops, sorry. We're going to use our old friend Ohm. All right, Ohm's law, where it says voltage is equal to the current times the resistance. That's going to be your Swiss Army knife to cut through all of this stuff. Going backwards, what we're going to do is we're going to use Ohm's law and the rules for these various circuits. And I'm going to review the rules as we go through. I've chosen a very simple one right now so that you can kind of see what's happening. So here we go. We're going to look at this circuit, the simplest one we can. And we know the voltage, and we also know the resistance. The only thing that we're missing out of Ohm's law is our current. So if I solve this, I'm going to take the voltage, 1.5 volts, and I'm going to divide it by the current, by the resistance, which is 125 ohms. If I divide that, I get this wonderful number of 0.012 amps. What that tells me is in this circuit, 0.012 amps is coming out of the battery. It goes through this whole circuit. Remember, this resistor represents all the resistors in the circuit. So it goes through all that stuff, and when it returns to the battery, it's 0.012 amps. Whatever leaves the battery has to come back to the battery. All right. So the game is this. You look at the circuit you just finished. Do you know every possible thing you can know about the circuit? I know the voltage, I know the current, I know the resistance. So I'm good to go. All right? I'm now going to go back over to my next circuit, the next most complicated circuit. And we said that this guy, and I forgot to leave my breadcrumb trail, there's that S, that this thing was in series. In series, since there's only one path around the circuit, that means there's only one current. And that current is the same in this resistor, it's the same in this resistor, it's the same in this resistor. So the one thing you need to remember is the current remains the same for everything in series. So I can go ahead and say, okay, there is 0.012 amps through that resistor. There's 0.012 amps in that resistor. And there's 0.012 amps in that resistor. That's what the series rule tells us. One path, same current for everybody. Okay, again, we play our game with Ohm's law. Ohm's law says if you know the voltage, current, and resistance. Well, I know the resistance, and I know the current for each one of these resistors. But what I'm lacking now is the voltage. All right? So now I can go through and calculate that voltage. So for instance here, the voltage is going to be equal to 0.012 amps times 50 ohms. And if you do that multiplication, if I get that parenthesis in there, you find out, let me change colors here so you can see it, I get a grand total of a voltage of 0.6 volts. I can do the same calculation down here, or I can use a little common sense. if I know that it's going to be 0.012 amps times 25 ohms, you certainly can do the math, or you can look at it and say, the current's the same in both of these, but there's half of the resistance in this one. So if this one was 0.6, this one's going to have to be 0.3 volts. And certainly if you do this calculation, you get 0.3 volts. All right, we can do that calculation for this one as well, or we can look at it one of two ways. In a series circuit, the rule is whatever voltage you put in, which was 1.5, it has to be used up or divided up by each one of these resistors. Well, if you look at it, you can see that this is 0.6 and this is 0.3. Together they make 0.9. So of the 1.5 we're putting in, 0.9 is being used. That would only leave 0.6 volts over here. And if you look at it, the multiplication for this resistor is going to be exactly the same as this resistor. It's going to be 0.012 amps times 50, which again is going to give you 0.6. So here's a check for you. In a series circuit, the voltage that you put in has to be used up by each of these resistors to add back up to 1.5, and indeed it does. Okay, so if we go back to our original circuit, this guy right here is really, there we go, these two guys in parallel. Now in parallel, the current divides, but the cool thing that stays the same is the voltage. So remember, this had 0.6 volts, this had 0.3 volts, this one had 0.012 amps passing through it, this one had 0.012 amps passing through it. So we now deal with these guys. If in parallel the voltage is the same for each branch, that means this guy gets 0.6 volts and this one gets 0.6 volts. Okay, again we play our game. We know the voltage and we know the resistance for this resistor. We need to find the current. And again, we're going to use our friend Ohm's law. I'll rewrite it now so it looks right. Okay. So I know the voltage and I'm going to divide it by 100. So I get 0.006 amps through that resistor. Now, again, there's a couple ways you can look at this to save time, or you can use some common sense. We know that coming to this node, there was 0.12 amps. If 0.006 of it goes here, how much has to go over here? Well, you would just subtract. And this is pretty easy math. You get, again, 0.006 amps. You could do the math, 0.6 divided by 100 again, and get 0.006. There's even a slicker way to do this. You notice that both of these resistors are the same. They're going to slow the current equally, if you want to think of it that way. So if this comes in and splits, because these resistors are exactly the same, the current will split evenly. So 0.006 and 0.006, it just gets cut in half. Now if these resistors are different, that current's going to be split up in a differing ratio, depending upon their resistances. So the resistance can tell you what ratio they're going to split. We'll look at one a little bit later. You notice that 0.006 comes this way, 0.006 comes this way. They add back up to make our 0.012. You've now found everything about this circuit that you can find. You found the voltage that each one of these resistors uses. You found the current that passes through each one of these resistors. You're basically done with this circuit. All right, so there's a simple one. I've got one that's a little bit more complex for you, not too much more. Let me move ahead here just a bit. All right, here we go. Bigger circuit. Certainly is not a pure parallel, and nor is it a pure series. How do we know that? Let's start on the plus side of the battery. As you follow it around, you come to this point right here. That's a node. So that means some current's going to go here, some current's going to go this way, some current's going to go this way. There's another node over here. So whatever's going on in this branch and whatever's going on in this branch, and don't let this corner fool you. It's just a bent wire. There's nothing magical about it. All right? So whatever goes on in this branch and whatever goes on in this branch, they meet back together here, and they come back together to make the current here that matches up with the current here. It hits this node and then goes back into the battery. So there's quite a few places here. There's quite a few junctions where the current splits and comes back together. So again, your game for you is to look at this circuit and say, okay, what's in series purely, or what's purely in parallel? And whatever you can identify, that's your starting point. It's kind of critical because if your starting point isn't good, it can throw you off completely for the rest of the circuit. The fact that there's a junction here tells you that there's a split. There's got to be some parallel involved. And so let's focus at this, right? When it splits, and this only goes through one a resistor on that branch, that's pretty good. That feels good. It splits, it only goes through one resistor on this branch. It split and it only goes through one resistor on this branch, but there's a problem. There's another node here. So there's a resistor over here. So this whole side here is not purely in parallel with this guy. But the cool thing is, this one goes through a single resistor, this one travels through a single resistor and comes back together. So this guy and this guy are purely parallel with one another. I want to put my P up here to remind myself that it's parallel. Okay? So how do I add resistors in parallel? It's that 1 over R. So 1 over, and again I'm going to drop my units real quick. I have 1 over 2 plus 1 over 3. Now we'll do this a little bit old school here. I think the common denominator, if I'm still can do my math, is 6. So that's 3 over 6 plus, and this is going to be 2 over 6. I believe that makes that 5/6. But remember, that's 1 over R. You got to reflip it. So R is going to be 6 over 5. Or, if I leave it as a decimal, it's going to be 1.2. And now I'm going to re-add my unit to it, kilo ohms. So that's really 1,200 ohms. Now I'm going to leave the kilo on here because it's going to help you in figuring out some numbers that are a little bit easier to handle that don't have as many zeros. So just bear with me and I'll show you some magic here in a minute. But the bottom line is we've combined these two resistors. We get to redraw our circuit again. So let me redraw the circuit next so we can see how this thing looks. It's now going to look like this. Still have that resistor there. We still have this resistor here, but those two that were on that diagonal now make this one resistor here, and we said that was 1.2 kilo ohms. Let me relabel this. This was 1 kilo ohm, and this was, is that right? Yep, that's 1 kilo ohm. This is 1 kilo ohm, and this is 1 volt. Okay, so we did parallel last. Now let's look again. Let's draw our nodes. All right. So it splits and goes through here, splits and goes through here. And on this branch, you'll see that there's one path that current passes through this first resistor and this second resistor. So this guy, those two guys are in series. They're in series. So we can talk about adding our resistors in series. Resistors in series, we just simply add them. So it's going to be 1 plus 1.2. Where you get a grand total of 2.2 kilo ohms. We get to redraw our circuit again. Yay! Isn't this fun? It's not so difficult once you learn the algorithm. It's just kind of tedious, more than anything else. And don't worry about wasting paper because there's plenty of it and we recycle. So make your circuits big enough that you can actually see what's going on and draw them. All right, so here's the next circuit we have, and I have a 1 volt again. So we look at it. I think I switched my battery. No, I didn't switch my battery. So if you come around, there are 2 nodes here. There are 2 junctions where the current splits. So the current splits this way, and the current splits this way. It passes through a single resistor. It passes through a single resistor and comes back together. That, for me, is my definition of parallel. So I'm going to put a P here. If they're in parallel, remember we add that really kind of funky way where it's 1 over R is equal to 1 over 1 plus 1 over 1.2. And again, I'll drop my units, I know. And if we go through and solve for that thing, you get a grand total, and you're going to have to reflip it, of 0.687 kilo ohms. Now here's a good rule of thumb for you to remember when you're doing these to kind of see if you're right. The total resistance here must always be less than the smallest resistor you were adding. So the smallest resistor was 1. This is less than 1. So you feel pretty confident that you've done this correctly. You're now down to the simplest circuit. I'm going to cram this guy over here because I don't need a great deal of room. So you've just found the total or the equivalent resistance for the circuit. It's equal to 0.687 kilo ohms. And this is 1 volt. So you've done what I call the compression phase. You've used your rules for series and parallel resistors to crush this down to the very, very, very simplest of circuits. So that's part of the way. But remember what the goal of this stuff is. It's to figure out what currents are passing through all the resistors, how much voltage is being used by them. This is how you design a circuit in a computer or any place else. You want to know what's going on in those elements long before you ever build the circuit. So we get to go backwards now and utilize all those rules all over again. And we're going to, again, be using Ohm's law. Right? Again, the Swiss Army knife of circuits. So here we go. The current is the one thing we don't know in this circuit. And it's going to be the voltage divided by the resistance. Now, I want you to notice something. You're dividing by kilo ohms. Or in other words, you're dividing by 1,000. Well, if you divide by 1,000, it becomes 10 to the minus third, which is the same prefix as milli. So if you keep this kilo ohm there, your answer is going to come out in something called milliamps. And it's going to make your math life a little bit easier. You're not going to have to write so many zeros and small numbers. So if you literally do the math of 1 divided by 0.687, you get 1.45 milliamps. Milliamps is a lot easier to carry around. What does that tell me? That tells me 1.45 milliamps is coming out of the battery, passing through the entire circuit that's represented by this one big resistor you've come down with, and that's what returns to the battery. Why is it important to know what comes out of the battery? It can give you some indication as to how long the battery will last. You might be wearing it down much quicker if you're drawing too much current from it. So it's kind of a useful thing to know, practically speaking. For you, it's the basis for everything else we do. Because now that we're through with this circuit, if you jump back over here, you know 1.45 milliamps is coming out of the circuit, or out of the battery, excuse me. It hits this junction. Some of it's going to go this way, some of it's going to go this way. So if you do the math on these two guys correctly, the current that you get here plus the current that you get here better add back up to the 1.45, because when it comes out of the junction, it's got to go back into the battery the same amount that it came in. So let's see. These guys are related in parallel. Here's where my breadcrumb trail comes into play. Again, the rule in parallel, you ask yourself what stays the same? Voltage stays the same. So that means that this guy gets 1 volt, and that means that this guy gets 1 volt. So they both have 1 volt because they are purely parallel. Again, we're going to use Ohm's law. We know the voltage and we know the resistance, but the one thing we don't know is the current. So current is going to be voltage divided by resistance. I want you to notice how I've written this. I've practically, for a reason, write the voltage over the resistance, because that tells me the operation I have to do. I'm going to divide. This is pretty easy. 1 divided by 1 is just 1. And when I divide by a killi, it becomes a milli. So I have 1 milliamp going through that particular resistor. Now, again, we can do the math again, or we can kind of use some common sense, what my dad called horse sense, right? If you've got 1.45 coming in here, and 1 milliamp is going this way, what's left over for here? Just subtract them. You get 0.45 milliamps. Well, if you prefer to do the math just to check yourself, 1 divided by a little bit more than 2 is going to be a little bit less than 0.5. So sure enough, that seems to work if I add and do the math. So again, what do you ask yourself? Have I found everything in terms of current and voltage that I can for this particular circuit? For this particular circuit, we're done. And we've actually found some answers. It's not an answer, but it's useful. 1.45 milliamps comes out of the battery. We do have an answer for this one. That's 1 milliamp goes that way. So now we have to say that, okay, this resistor is really these two resistors related in, and here's our breadcrumb trail, in series. So you have to ask yourself your rule again. What stays the same in series? Current. So that means when the current comes through here, that 0.45 milliamps comes through here, and that 0.45 milliamps also goes through here. All right, so the rule tells us that these guys are going to get the same current because it's a single path, unbroken, single path. Again, you ask yourself, do I know everything? Well, I know the resistance and I know the current. So if I know the resistance and the current, I can find voltage. Again, I'll show you my little trick. Typically, I don't write the current down here. I write it next to it. Because again, that tells me what operation I'm going to be doing. That tells me that voltage is going to be equal to current times resistance. Again, the math here is not too hard. If you do the math, and I'm going to change the color just so you can see it, 0.45 times 1 is 0.45, and a kili and a milli are direct opposites of one another. One's 10 to the third, one's 10 to the minus third, so they kill each other. So you're just going to left with volts. So that guy gets 0.45 volts of the 1 volt that this guy said he was getting. Again, you can use a little horse sense here. If 1 volt is what these two together were getting, and 0.45 of it's here, well, hopefully if I do the math correctly, the rest of it is 0.55 volts. And again, if you take 0.45, which is a little bit less than a half, and multiply it by 1.2, which is a little bit more than 1, it makes sense that it comes out a little bit bigger than a half. Okay? I know this is tedious. Hang with me, bud. I have no clue how you're feeling, so if you want to hit pause and snooze or get yourself a drink or eat a sandwich or peanut butter and Nutella, that works for me. I'm going to keep going because you can pause, but I can't. So we're going to go back one more slide. And this guy is done. But this guy right here was really represented by these two guys that are in parallel. And if you remember again our rules, what stays the same in parallel? It's voltage. And remember that was 0.55, so that means this guy gets 0.55 volts and this guy gets 0.55 volts. Well, if I know the voltage and I know the resistance, that means I can find the current. And if I take 0.55 and divide it by 2, I get roughly, and this is an approximation, 0.28 milliamps. Remember coming through here was 0.45 milliamps. And remember what was coming this way was 1 milliamp. So again, we can use some horse sense, and we can also use our math to check us, or vice versa, whichever you feel most comfortable with. If 0.45 comes to this node and 0.28 goes this way, what's left over to go this way? Well, 0.45 minus 0.28, I think, if I do my math correctly, it's 0.17 milliamps. It goes down here, this one goes down here, they come back together, so the 0.28 and the 0.17 makes 0.45, and that 0.45 and the 1 come back to make 1.45 milliamps. So it seems like everywhere, everything's checking out. Our numbers add back up, and everything that we've done seems to make sense. Another thing that I want to point out to you going forward, you'll notice that the first thing we saw was a parallel. If you do everything in the circuit that is purely parallel, all at the same time, so there may be even more than one parallel in there, the next thing you're going to see in the very next circuit you do is you're going to see a series. If you do all the series in that circuit that you can possibly do, the very next thing you're going to see is a parallel. So what you'll notice is there's a pattern. If you start with parallel, the next circuit, again, you have to do all of them. Anything that's series or anything that's parallel, you must do them completely. It's going to alternate from series to parallel, from series to parallel. So that's, again, another little check that you can kind of go through and make sure that you're reducing everything as you need to do so. Okay, so here are two examples that were out of the worksheet. And I think you have that in your possession, but I'm also going to make sure you have access to that. I want you to practice these or re-practice things because I know it's been a while since you've done them. We'll take a look at those, and provided you're okay with those, we'll move you on to the next type of circuit analysis, which will be in the next video. Okay, so that one's done.